Today we will talk about joint distributions. This is part two of a two-part series. The goal would be to study expected values and variation when dealing with more than one random variable. Suppose x and y are two random variables. Um we will assume that either both x and y are discrete or both x and y are continuous. In this setting, let p x comma y be the joint probability mass function for x comma y if both x and y are discrete, and fx comma y be the joint probability density function of x and y if both x and y are continuous random variables. Now, suppose h is a function of x and y, then we can define the expected value of h x comma y. This is a random variable. The expected value is defined as the sum over all pairs x comma y inside script x cross script y of hx comma y times px comma y if x and y are discrete, and it's the double integral hx comma y times the probability density function if x and y are both continuous. We will use the expected value definition to talk about covariance and correlation of two random variables. We want a way to measure relationships between x and y, and towards this goal, let the mean mu x be the expected value of the random variable x, and mu y be the expected value of the random variable y. In this setting, we can define the function hx comma y as x minus mu x times y minus mu y. This is the product of the deviation of the random variable x and y from their respected expected values. The function h satisfies some interesting properties. Note that if we have large values of x associated with large values of y, that is, whenever x minus mu x is positive, we have y minus mu y to also be positive. And if small values of x are associated with small values of y, which means that x minus mu x less than 0 implies y minus mu y less than 0. In this setting, you will notice that hx comma y would end up being a positive function. The product x minus mu x times y minus mu y is always going to be positive because both the terms on the right hand side of this equation are either both positive or both negative. Now, if large values of x were to be associated with small values of y, that is, if x minus mu x greater than equal to 0 implied y minus mu y to be less than equal to 0, and if large values of y were to be associated with small values of x, that is to say that y minus mu y greater than equal to 0 implied x minus mu x to be less than equal to 0, we will have that the function h of x would always be negative. That is, the product x minus mu x times y minus mu y is going to be less than equal to 0. And this is the case because the terms on the right hand side of the equation have opposite signs. A consequence of this discussion is that the expected value of the random variable h x comma y, defined as the product of x minus mu x times y minus mu y, would be a good candidate to measure a certain relationship between x and y. We will make this precise next. We define the covariance of the random variables x and y as the expected value of x minus mu x times y minus mu y. You can simplify this as the expected value of x times y minus the expected value of x times expected value of y. This is the expected value of the product of the deviations of x from the expected value mu x and y from its expected value mu y. The covariance can be defined in the discrete setting as the following double sum, and in the continuous setting as the double integral x minus mu x times y minus mu y times fxy times dx dy if x and y are continuous random variables. Note that if x equals y, the covariance of x comma y would be the covariance of xx, which is exactly the variance of x. If x and y have a strong positive relationship, that means large values of x are associated with large values of y, and small values of x are associated with small values of y, we will get the covariance of the random variables x comma y to be positive. In a similar way, if x and y were to have a strong negative relationship, that is to say that large values of the random variable x are associated with small values of the random variable y, and large values of the random variable y are associated with small values of the random variable x, we will get that the covariance between the random variables x and y will be negative. This is to say that if covariance is positive, we can say that x and y are positively associated, and if the covariance between x and y is negative, we can say that the random variables x and y are negatively associated. Note that even though this gives us a sense of association between x and y, this is not a good measure of association because it depends on the units in which x and y are measured. That is, we can make the covariance of x and y to be arbitrarily large or small by changing units as long as the covariance is non-zero. To take care of this situation, we will introduce the correlation coefficient of x and y. Let sigma x be the square root of the variance of x. This is the standard deviation of the random variable x, and sigma y be the standard deviation of the random variable y. To make the covariance unitless, we will divide it by the product sigma x times sigma y. The correlation coefficient of x and y is therefore defined as rho x comma y equals the covariance of x comma y divided by the standard deviation x times the standard deviation of y. Some things to note over here are that the correlation coefficient does not depend on the units in which the random variables x and y were measured. The correlation coefficient will always be a number that lies between -1 and 1. If a and c are real numbers which are both positive or both negative, the correlation coefficient of ax plus b and cy plus d will be the same as the correlation coefficient of the random variables x comma y. In particular, if y had a perfectly linear relationship, that is y was equal to ax plus b, the correlation coefficient of x comma y would be equal to either plus minus 1, and the sign would depend on the sign of the number a. This is to say that the correlation coefficient measures the degree of linear relationship between the random variables x and y. If the correlation coefficient is close to 1, we can assert that there is a strong positive linear association between the random variables x and y. And if the correlation coefficient is close to -1, we can assert that there is a strong negative linear association between the random variables x and y. If the correlation coefficient is 0, we will say that the random variables x and y are uncorrelated. That is to say that there is no linear relationship. Note that this does not mean that there is no relationship. there can be a relationship which is non-linear in nature. If x and y are independent random variables, the covariance of x and y is going to be equal to 0, and as a result, the correlation coefficient of x and y is going to be 0. Note that the correlation coefficient equal to 0 does not imply that the two random variables x and y are independent. Finally, we will recall the golden adage, which is that correlation does not imply causation. It only implies that there is a positive or a negative association between the two variables of interest. It is possible that there is an underlying variable that we are not analyzing that is causing the positive association between the two variables that we are actually studying. Finally, note that the correlation coefficient equals covariance divided by the product of the standard deviation. We can rewrite this formula to get the covariance of x comma y to be equal to the correlation coefficient times the product of the two standard deviations. We finish up this video by talking about linear combinations of random variables. Suppose we have n random variables x1, x2, x3 up to xn. And for each of these random variables, suppose we know their expected value to be mu I for I going from 1 through n, and the variance of xi to be sigma I squared, where I goes again from 1 through n. Now, if we had n real numbers, a1, a2 up to an, we can define the linear combination of x1 through xn as y equals a1 x1 plus a2 x2 plus a3 x3 up to an xn. We might want to ask a question: what is the expected value of y and what is the variance of y? The answer to this question is provided by the following theorem. The expected value of a linear combination is going to be the linear combination of the expected values. That is, it is going to be the sum of a1 mu1 all the way up to an mu n. And the variance of a linear combination of random variables is going to be a sum, a double sum of covariances xi comma xj, where the coefficients are ai times aj. In particular, note that if x1, x2, x3 up to xn were to be independent random variables, the variance of the linear combination would be equal to a1 square times the variance of x1 plus a2 square times the variance of x2 all the way up to an square times the variance of xn. Note that for two random variables, say z equals ax plus by, we can talk about the expected value of z to be equal to a times the expected value of x plus b times the expected value of y. And the variance of z is going to be a square times the variance of x plus b square times the variance of y plus 2ab times the covariance of x comma y. In particular, when a equals 1 and b equals minus 1, we are looking at z equals x minus y. We will have the expected value of x minus y to be equal to mu x minus mu y, and the variance of x minus y is going to be sigma x squared plus sigma y squared plus 2 times the correlation of x comma y times sigma x times sigma y. There are a few subtleties one should keep in mind when we are talking about the sum of two random variables. For example, if we were to take the sum of the random variable x with itself, the resulting random variable would be x plus x, and that is not the same as the random variable 2 times x. To summarize today's video, we spoke about expected value for a function of two random variables. We defined the covariance of two random variables, the correlation coefficient of two random variables. We saw how these give us information about the extent of linear relationship between the two random variables x and y. Finally, we introduced the idea of linear combinations of random variables, calculated the expected values and variances of linear combinations of random variables. This is all for now. Take care of yourselves, and I will see you around.